Hello everyone and welcome to Engineer Tomorrow's 15th video in the thermodynamics video series. So the topic for today's discussion is water vapor an ideal gas? Can we use the ideal gas equation of state to characterize water vapor's properties? And the way we'll be addressing this is through the use of the compressibility factor. So in short, the answer is it depends. You may say, oh man, you had me fooled by the title of this this video. I thought you were going to explain, is it or is it not? A straightforward answer. And the reason it depends is because it depends on the compressibility factor. Okay, and we'll call that Z for now. Okay, so before our discussion, let me just prepare you guys for this discussion. Let's say we have the temperature versus specific volume plot. And it may seem that I'm always starting my conversations with this plot of the liquid vapor dome, but it's actually very helpful in addressing a lot of the discussions we're currently having. So I'm going to draw this line right here in the superheated vapor region, okay, which is at an angle to the specific volume axis. Okay, so what you see here is a transition region between an ideal gas. In our previous video, we discussed that the ideal gas has to be, away from the liquid vapor dome, over in the superheated region, and if it's very close to the dome on the vapor side, it is a vapor, but it is not considered an ideal gas. Okay, so in this plot, what we have is constant pressure lines, which we've discussed in previous videos. Okay, so I'll just draw a couple. Okay, and as it turns out, below a certain pressure, so let's say that our pressure is low. Okay, we're a vapor and our pressure is very low. So if our pressure is low, you may remember that if your pressure decreases, with decreasing pressure, you go down in the temperature versus specific volume plot. So you would be somewhere in this region over here. Okay, so as you can see, you're getting very close to the transition region between a vapor and ideal gas. Okay, so for low pressures, it is thought that water, I'll just say Ig for ideal gas, is a good assumption. Okay, and the reason it's a good assumption is because, as I said, we're in that regime where it's very close to becoming an ideal gas. It may not be exactly an ideal gas, but it's a good assumption. Okay, but say, so before we move on to the other extreme, a scenario where this would be valid would be, let's say, in air conditioning systems. Okay, or maybe you're studying water vapor in the air, using relative humidities and things like that. It's a relatively good assumption to make that the water vapor behaves like an ideal gas. You may have to do some further analysis by determining the compressibility factor, which we'll show in this video, but generally it's a good assumption. So on the other side, let's say that our pressure is high. Okay, then the water ideal gas assumption is bad. Bad assumption. Okay, and somewhat, you can see that from this plot. As you start going higher in pressure, you start seeing that there's a lot more space, where you're in the vapor regime instead of in the ideal gas. Especially if you're playing with the area close to this liquid vapor dome, as is usually done in thermodynamic processes. So somewhere you would see this would be a boiler. Okay, so for like steam power plants and things like that, the boiler generally works around this area, and this boiler, you cannot assume that water is going to behave like an ideal gas. Your answer will be really far off if you actually do make that assumption. Okay, so now that we've kind of discussed that, let's kind of define what the compressibility factor Z actually is. So the compressibility factor is actually the pressure times the specific volume divided by the ideal gas constant of a specific gas times the temperature. Okay, and from our previous video, this relationship actually came from the pressure times the volume is equal to the number of moles times the ideal gas constant times the temperature. And what you did is you actually non-dimensionalized this value. So you said PV over N R bar T is equal to a number. Okay, well, if the ideal gas assumption is correct, ideal gas constant so for this ideal gas constant to be true, you would have to have Z is equal to 1. Okay, because if this side is going to be equal to this side, if you divide it over, you're going to get a 1 for this non-dimensional number over here. So you can see that if you have a specific pressure and a specific volume, and you have a given temperature and you're trying to find the amount, this ratio may not necessarily give you the value of 1. So you'll vary between high or low compressibility values, and that'll kind of give you an idea of how far you are from the ideal gas assumption by considering how far the compressibility factor is from 1. So a different way we can write this is the compressibility factor is equal to the specific volume of the actual water vapor divided by the specific volume if we assumed that the water vapor behaves like an ideal gas. So this value over here will be RT over P. Okay, and remember that this is the ideal gas constant for a specific gas, and then this value, we can determine by taking our measurements as well. So you may say, okay, well, how do we compare this compressibility factor to different gases? So you may get, for a given temperature or for a given pressure, your compressibility factor will vary significantly if you looked at water or if you looked at mercury. Let's say mercury. So although this is true, it was determined that you can actually look at your reduced pressure and reduced temperatures Okay, and what I mean by this is your reduced pressure is equal to the pressure you have at a given condition divided by the critical pressure. Okay, and that's the pressure at your critical point. So let me just show you where that is. That would be right at this critical point, right up there. Okay, and your temperature, your reduced temperature is equal to your you're given the temperature you have divided by the critical temperature. So it's the temperature at that given point as well for a given gas. So what scientists actually did was they had, they created this plot. Okay, and they said, let's plot the compressibility factor. Okay, and this is at 1. Okay, and we'll plot it this way. This is 1, just so you have an idea where it is. And what they did was they plotted this compressibility factor by the reduced pressure for different reduced temperature ratios. So what they ended up finding was, let me plot. Okay, this is H2O, and this is mercury. I'm gonna write down mercury. Okay, so they found, for plotting different values, they got something like this. Alright, so right now I'm just plotting the mercury values. Okay, and for the water values, they got something like this. Okay, and if you went in and actually did this for a lot of different liquids or gases, you would actually notice that there's a similar trend between them. Okay, and this relationship was determined empirically, and can be used to see, I guess, where you would have good assumptions for an ideal gas. So if we were looking at this plot and we wanted to know where is it a good assumption, we would look at this range right here. So let's say our cutoff is 0.9. So we want to be above 0.9 to obtain ideal gas assumption validity. Then we would say, okay, well, our given pressure, reduced pressure, needs to be this, less than this or greater than this for this temperature, reduced temperature value. Okay, and just like I plotted it for one reduced temperature value, you can plot it for multiple, and what you would see is something like this. Okay, and then you would get other values like that, and they would approach 1. Okay, so that is increasing reduced temperature. Okay, so what do we know from this plot? Okay, so if our temperature ratio is greater than a certain amount, then it's a good assumption. So this certain amount actually becomes 2. Okay, and this is except when your reduced pressure is much greater than 1. So except for because some strange behavior begins to happen over here. Okay, and it's also a really good assumption that we have an ideal gas if your reduced pressure is much less than 1. Okay, as you can see in this region over here. And as you increase your reduced temperature, this starts extending a little bit farther out as well. So I hope this was helpful in allowing you to kind of understand, when you can use the ideal gas assumption and when you can't. If your professor asks you why are you using the ideal gas equation, then you can answer him by saying, okay, well, my compressibility factor was above 0.9 or above 0.95, so I thought it was a good assumption. And this will wow your professors, and they'll be like, oh, this guy actually knows what he's doing. So I hope that was helpful. Please leave some feedback in the comment section. If you guys need any help or need me to clear anything up, I'd love to answer your questions.